Hello, this is Jake Abbott. In the last few videos in this sequence, we've been talking about using state feedback from, if you have full state knowledge, to control our system's eigenvalues. We've been talking about making a state estimator or observer to estimate the states if we don't have full state information. We've seen that we can add those two systems together, and there's this separation principle that lets you design the eigenvalues of the controller and the eigenvalues of the observer separately, and your combined system is just those two eigenvalues combined, which is a really beautiful result. But up until now, everything we've been doing has been assuming single input, single output systems. So we've been assuming something like this, where we have n states. So our state vector has been many things, and A is an n by n matrix. But we've been considering single inputs, U, and we've been considering single outputs, Y. And even in the tracking problem, we've been talking about single input, single output systems. So what we want to do now is we want to generalize this to multi-input, multi-output. So instead of U being a single thing, we want U to be a p by 1 vector. So we have p different inputs, so which means B must be an n by p matrix, and we want Y to be some outputs, and let's say that's a q by 1 vector, and so q and p aren't necessarily the same things. We may have different inputs than outputs. So then if this is an n by 1 vector, then this must be a q by n matrix. The nice thing about extending this to multi-input, multi-output is that all of the really important results still hold. So let's think about what some of those important results were. One was, we said this system A minus bk, b, this pair, is controllable. So controllable if and only if the pair AB is controllable. So that basically means we do the analysis of controllability on our original system, AB, and if that system's controllable, then our closed loop feedback method is also controllable. This holds regardless of the dimension of B and therefore the dimension of K. So that's a nice result. It's also true that if this is controllable, then we can place, so let's call this sort of result 2. If the pair AB is controllable, then that implies we can place eigenvalues wherever we want. Place eigenvalues wherever we want using K. So now K is this going to be, let's think of the dimensions here. So if I have A minus bk, and A is n by n, then this bk must be n by n to make the dimensions work. This is n by p, so K must now be a p by n matrix. So it's still true, I can place the eigenvalues wherever I want using this p by n k matrix. We also had this result, that's the dual result, which said that the pair A minus LC, C, is observable if and only if this pair AC is observable. So we basically said if our original system is observable, then after we do this closed loop observer, then that system is also going to be observable. That still holds, and we can still place the eigenvalues. Place eigenvalues of A minus LC wherever we want using L. And if you think about dimensions of this, A minus LC, this is n by n, so LC must be n by n. C is this q by n thing, so L must be an n by q matrix of real numbers. So all of these really important results hold. We can place the eigenvalues wherever we want using these basic state feedback methodologies. Now, how do you do that state feedback? If you're doing it for single input, single output, there were these. You can do it explicitly if your system is small enough. You can do it explicitly algebraically. That's one method. Another good method is that you first convert your system into controllable canonical form. Once you're in controllable canonical form, there are very simple algorithms to find the values, to find the K matrix when you're in controllable canonical form. And then the last thing you have to do is then convert your K matrix back using the same equivalence transformation that you used to convert it to controllable canonical form. That method still holds in this multi-input multi-output case. The method becomes a little bit more complicated, and the Chen book has a very clear explanation, I think, on how you extend this method to multi-input multi-output. So once you have a method to figure out the controller gains using this controllable canonical formulation, it turns out you can, using the duality of controllability and observability, you can just apply that method directly for observers. So if you have some system A minus LC and you want to place the eigenvalues of that, you can recognize that this matrix, if you just take the transpose of this matrix and then distribute that transpose, you'll get A transpose minus LC transpose, and if you distribute the transpose through a multiplication, you distribute the transpose and then reverse the order of everything, so that looks like minus C transpose L transpose. And if you look at the dimensions of this, this is an n by n thing, and this C was originally Q by N, so C transpose is N by Q, and then L is Q by N, and all of a sudden, if you remember back to what we had when we had A minus BK, this looked like N by N, B was N by P, and K was P by N, but there's nothing special about the number P. So this system here and this system here have the exact same form as each other. So once you have a method to take something that looks like A minus BK and solve for K using this controllable canonical form, you can apply that same method to a system that looks like this, where everywhere you would have an A, you have an A transpose, and everywhere you'd have a B, you'd have a C transpose, and everywhere that you'd have a K, you'd have an L transpose. And when you're done, so you would just basically plug this in, so you'd plug in A transpose for A and C transpose for B, and then you would solve for K, and then the very last step after you figured out K is you would just say, well, L transpose is equal to K, which means L must be equal to K transpose. So you can just take the method that you already have learned that Chen clearly explains for the multi-input multi-output how do you find K algorithm, and apply it for finding the observer gains L just as well. Now the truth is that this becomes very difficult in the multivariable case, and while these methods do exist, this is probably something that you're going to want to do numerically if possible, and using MATLAB functions like the MATLAB function place is going to be, I'm saying place, the MATLAB function place will let you automatically find these values of K using A and B, and so you can use that algorithm to solve for this and also for this using this substitution here. So sort of to summarize, all of these basic results about single input, single output cases apply to multi-input, multi-output, all of the really fundamental results. I think one thing that still needs to be said is, what about tracking? When we basically were using for single input, single output, a closed loop method that says, let's make our input U some reference minus K times X. And that would let us have this was when we had one input U, and then reference was also one thing. And this would let us control the gains the way we want, or excuse me, control the eigenvalues the way we want. And we said the best way to choose R, we're going to figure out some DC gain of our system. And then the way that we choose R is we say, let's make R be Y desired divided by the DC gain of our system. And then if we do that, we know that the steady state value of our system is equal to the DC gain of our system times R, and so this would let our steady state value of our Y be equal to our desired value of Y if we implemented this algorithm. It worked really well, and we said this works provided, you know, GDC is not equal to 0. In the case of a DC gain of 0, this tracking problem doesn't really make sense, but as long as we're not dividing by 0, we're going to be fine and this will work. So this all makes sense if you're in single input, single output land, but we're not there anymore. Now we have multiple inputs. So this is a p by 1 vector. And so R is now also a p by 1 vector of things. And so in this case, and then let's think about Y. What does Y look like? That's a q by 1 vector. So we might not even necessarily have the same dimensions of R and Y. So you have to think clearly about what do you mean here when you're talking about tracking. We clearly have some y's that we would like to control, and we think we would like to make those y values go to values we want by setting r appropriately. But if you don't structure your problem correctly, it may be sort of an ill-defined problem to begin with. Like, for example, let's say you have a 3x1 vector, y1, y2, y3, and you have a 2x1 r vector. So we have 2 inputs and 3 outputs. I think it's reasonable to ask yourself, is it possible to set all 3 outputs to values we want using only 2 inputs? If we have less inputs than outputs, is it possible to establish all of those the way we want? It may be reasonable to think that isn't really possible. It also may be, what if instead we have 2 inputs but only 1 output? We have 2 different inputs and 1 output. Which of these inputs should we be setting to y desired over DC gain? Is that really a well-defined problem? In the special case where you have 2 inputs and 2 outputs, it's somehow reasonable. It seems reasonable to think that there might be some sort of mapping, but it isn't clear unless our system is like perfectly diagonal. It isn't clear, does R1 correspond to Y1 and R2 correspond to Y2? I mean, these things aren't completely obvious. So let's think more abstractly. If we think of the transfer function of our system, so we say our output y of s, and this is going to be now a vector of outputs. We know how to do the transfer function of our system. It equals C times the matrix Si minus, and now this is our closed loop A matrix, so this is going to be A plus BK, so I'm minusing A minus BK. That thing inverse times B times, this will be our reference. And so this is a big p by 1 vector of inputs in Laplace domain. This is a big q by 1 vector, q by 1 vector of outputs in Laplace domain. So this is a big transfer function matrix where each element is a transfer function, but this is a big q by p matrix. So when we did the DC gain, we recalled this idea that the DC gain ultimately comes from time going to infinity, which using final value theorem is the same as s going to 0. So we said to find the DC gain, what we did is we set s equal to 0, and so we said let's apply this to sort of the DC gain in matrix form. This isn't a scalar anymore. It's going to equal c, so I'm setting s equal to 0, so it's equal minus a plus bk inverse b. Now, first of all, we should ask ourselves, does this matrix inverse exist? And because we're making our system stable, we know what all of its eigenvalues are. They all have negative real parts. And so none of our eigenvalues are 0, so our determinant isn't 0. So this matrix is always going to be invertible for us whenever we've made a stable system. So the matrix inverse is no problem. But again, this is an n by n non-singular matrix. So it's a square matrix that's full rank. This is a p by 1 matrix, and this is a q by 1, or excuse me, this is a q by n matrix, and this is a u is the p by 1, so sorry, this is an n by p matrix. So there's a result that says if you take any matrix and multiply it by a non-singular matrix, you don't change the rank. So if I take this B matrix and I multiply it by this non-singular n by n matrix, the rank of these two multiplied together is the same as the rank of B. The same thing goes for multiplying C in this matrix. So I'm not going to lose any rank by doing that, but I have to drop rank as if P is a number less than n and if Q is a number less than n, I have to drop rank at some point. So let's start thinking about when would it make sense to say, does this exist? Because if it did, then we truly could say, okay, I'm just going to take my DC gain, I'm going to invert it, I'm going to times that on the left side of both of these equations. So I'm going to times my DC gain by some desired y. Now this is a big vector, a q by 1 vector, and this would be a if this inverse exists, it already implies I have a square matrix, so it already implies that Q and P are both equal to n, right? So I have an n by n thing to have that even make sense. And in the event that exists, I can apply my single input, single output result directly. So I just take my desired y, I multiply it by the inverse of my DC gain, and that's how I establish R. And so that implies a couple of things. It implies, first of all, I have a square system, which means I have the same number of inputs as I have outputs, and that number of inputs and outputs is going to be equal to n. The number of inputs and outputs should be equal to Q. So if I have, I'm saying that P and Q are both equal to each other. Sorry, not n by n. This was a typo. So I'm basically doing a Q by Q matrix. So I have this input y. I'm going to multiply this y, which is a Q by 1 thing, and I keep wanting to write Q by n. I have this Q by 1 thing. I'm going to multiply it by this Q by Q thing, and then I'm going to get a Q by 1 thing. So in the event you have the same number of inputs and outputs, but it doesn't matter if they are equal, if they're equal to n. It just matters that they're equal to each other. Then this sort of method will work, and that this matrix exists. So it's not sufficient just that I have the same number of inputs and outputs, but it matters that this inverse exists. For the inverse to exist, it has to be square. So that's sort of the first step. But when I have this full rank matrix. When I multiply B by it, and then multiply C by that matrix, I have to have that resulting Q by Q matrix, I have to have that matrix still be invertible. So depending on what your B and C matrices are, you may or may not build a system that is invertible. So you have to think about the types of systems that would result in that happening. And this comes down to, do you have are you asking well-defined problems? So for example, let's say two of your states are position and velocity of some mass. Would it be reasonable for you to say, I would like my position to go to 5 and I would like my velocity to go to 10? The fact you're saying I want my position to go to 5 is the same thing as saying I want my velocity to go to 0. So if you ask for any velocity other than 0, it would be unreasonable for you to think that you could achieve velocity and position simultaneously. So those sort of strange cases where you're basically asking your system to achieve something that it couldn't possibly achieve, those are going to be the cases where this GDC inverse matrix is not invertible. But if you're asking well-defined problems, so for example, let's say you have a system that's a 2-link robot arm, and your states are the position and velocity of joints 1 and joint 2. It would be reasonable for you to say, I'd like to design a control system that joint 1 goes to 10 degrees and joint 2 goes to 50 degrees. That would be a reasonable request. And that would be the type of system. So that, think about what your C matrix and your B matrix would look like in these sort of cases. That would be the type of system where it may be that you can in fact get an invertible G matrix, and this sort of algorithm would work. So sort of you have to take these problems case by case in this way, and make sure you're always, first of all, always asking for achievable systems. Don't ask for a system that physically doesn't even make any sense. And if you start with that assumption that you're asking for physically realizable systems, it's often the case that these sort of results hold. Now, I think another special case is the case where this matrix is not square, but you have more inputs than you have outputs. If you have 5 different inputs, but you only care about 2 different things, it seems possible that should also be achievable. And so rather than, and I think that is the case in many cases, that's also achievable. And so in this case, rather than doing an inverse, you have to do a pseudo-inverse. So a pseudo-inverse, what that does is it says, I can't invert it because it's not a square matrix, but if I have a matrix, so let's imagine what I just said. So let's think of what my G looks like. So I have Y that's a Q by 1 thing, and so let's say let's say my y is like a 2 by 1 thing, so here's y1 and y2, and my input's like a 5 by 1 thing, so I have r1 all the way down to r5. So this matrix is a 2 by 5 matrix, like this. So it's a long flat matrix. In cases like this, it may be the case that there is some combination of r's to achieve the desired y's, but not a unique combination. There's actually lots of different r's that could achieve the desired y's that you want. In this case, if this is my DC gain matrix, this is a case where the pseudo-inverse, sometimes we use like a dagger to describe pseudo-inverse. The pseudo-inverse of this will give you one of the possible solutions of r that will let you achieve y. And it's actually, if there's infinitely many solutions of r, you have to find a good way to choose r. So it chooses the r so this is a 5 by 1 vector, let's say. It chooses the vector that has the smallest norm. So it tries to use the smallest inputs possible. And so instead of commanding y desired times the inverse of this, I'll take y desired times the pseudo-inverse, and I'll set that equal to my reference. So this is also a possibility if you have more inputs than you have outputs. But again, it's conceivable. Just because you have more inputs than outputs doesn't necessarily mean there is some solution to achieve this. To find that, it's very easy to see that. So in my case here of a 2 by 5 matrix, I need this matrix to be rank 2. If this matrix is rank 2, then this will definitely work and I will achieve what I want to achieve. If this matrix is not rank 2, or full row rank I should say, then even this method won't exist. And this pseudo-inverse operation also exists in MATLAB. It's called pinv for pseudo-inverse, and you would just do pinv of GDC, and MATLAB would let you find these values.